hit this jagged mineral rock with an invisible ultraviolet laser, and it instantly erupts into brilliant neon greens and reds. The rock itself doesn't contain a hidden battery, and this light isn't a reflection. The laws of physics dictate that this new, highly visible energy cannot simply appear out of nowhere. This is photoluminescence. It is the mechanism that makes the security strips on your currency glow, powers the fluorescent dye in a highlighter, and lights up plastic stars on a bedroom ceiling. What looks like a static glow on the surface of these objects is actually the collective output of trillions of high-speed collisions happening deep inside the material's atomic structure. To understand how one beam of invisible light can manufacture another beam of visible color, we have to shrink down to the scale of a single atom. Inside the atom, electrons are confined to strictly defined energy tiers. When an electron is at rest in the lowest possible tier, it sits in its ground state. When an incoming photon strikes the atom, it transfers its payload of energy directly into an electron. That sudden influx forces the electron to instantly jump up into a higher, unoccupied tier. The atom cannot sustain this configuration. Highly unstable at this altitude, the electron immediately seeks equilibrium. Before dropping, it vibrates against its surroundings, bleeding off a tiny fraction of its newly acquired energy as heat. Because of that heat loss, the electron holds less energy than when it first jumped. As it finally plummets back to the ground state, it sheds the remainder of its payload by ejecting a brand new photon. Because this emitted photon carries less energy, its wavelength is stretched. That mathematical difference between the energy the atom absorbed and the heat it lost is what shifts invisible radiation into the visible colors we see. This entire drop sequence usually happens in a fraction of a nanosecond. Turn off the UV light, and a fluorescent dye goes dark instantly. Yet certain materials can maintain an eerie glow for hours in total darkness. This Jablonski diagram maps these varying timelines. In fluorescence, the excited electron maintains its original quantum orientation, called a singlet state. Its path back to the ground state is clear, so it falls immediately. But in phosphorescence, the electron drifts horizontally into a different energy column, a triplet state. During this inter-system crossing, the electron physically flips its quantum spin direction. This creates a conflict with the Pauli exclusion principle, which prevents an electron from dropping into a ground state that already matches its spin. The pathway back is effectively locked. The electron is trapped in this elevated position. It cannot return home until it flips its spin back to its original orientation, a rare maneuver that forces the material to bleed out its energy at a glacial pace. The lingering glow of a phosphorescent object is visual evidence of trillions of electrons executing this improbable quantum flip to finally escape their trap. When atoms are isolated, their energy levels remain distinct and sharp, but pack trillions of these atoms into a rigid semiconductor lattice, and their electronic orbitals begin to overlap. To satisfy quantum rules of spin, these levels shift and crowd together, eventually merging into broad, continuous highways of energy called valence and conduction bands. When light strikes this solid lattice, it rips an electron from the lower valence band and throws it across the gap into the conduction band, leaving behind a positively charged void or hole. Together, they form an exciton. When that electron eventually loses momentum and falls back across the gap to recombine with the hole, it fires off a photon. Because this light is dictated entirely by the physical width of the gap between these bands, measuring this specific glow provides a flawless readout of the semiconductor's internal architecture. Because this emission is so precise, laboratories use photoluminescence spectroscopy as a microscope made of light, a method to inspect solid materials without physically cutting them open. This graph displays a material's light emission. By analyzing the exact spectrum of light that bounces back, researchers detect single missing atoms or chemical impurities. A structural defect alters the electron's fall path, forcibly changing the wavelength of the photon it emits. Spectroscopy uses this process to force the material to broadcast its own microscopic flaws as a readable confession of light. This data allows engineers to verify the absolute purity of silicon wafers required to build highly efficient solar cells. It guides the precise tuning of band gaps necessary to manufacture vivid OLED displays and the laser diodes found in fiber optic networks. It also enables the design of specialized biomedical markers engineered to seek out and illuminate specific microscopic diseases inside the human body. Material science is now moving beyond observing these reactions toward active construction with quantum dots. In quantum dots, a nanoparticle's physical size dictates the color of light it emits. Adjusting this diameter lets scientists custom-build light signatures atom by atom. We began by watching a gray rock glow under a laser, witnessing a process we didn't yet understand. Today, by decoding this quantum fingerprint, we have gained the ability to dictate exactly how matter interacts with light, turning a curious natural phenomenon into a precise tool for building the next generation of technology.